So today we are going to look at a problem involving a block that's resting on an inclined plane. So if you see here, this is the inclined plane in question, and here is the block. There is friction on the inclined plane with a friction coefficient equal to mu. And we want to answer these three questions. What is the acceleration of the block? Under what conditions does the block not move? That is, it is stationary. And if it's moving, how long does the block take to slide down the inclined plane uh, a distance L along it? So let's look into these three problems. So the first thing we want to find out is how the forces act on this particular block. The first force that we want to consider is the weight of the block that acts straight downwards. So now if you see here, here there is a right triangle. This angle is theta. This angle is 90 degrees. Therefore, this angle is 90 minus theta. Now, if we want to resolve this component, resolve the weight along two components, one that's perpendicular to the inclined plane and one that's parallel to the inclined plane, we see here that this angle here is 90 degrees. Therefore, if this angle is 90 minus theta, this angle is theta. So now what we do here is we take this weight and we resolve it in a direction that's normal to the inclined plane. When we do that, this component comes out to be mg cosine theta. Now, obviously we know that this angle is 90 minus theta. Therefore, the component of the weight that acts parallel to the inclined plane is mg times cosine of 90 minus theta. It's mg sine theta. The thing to note here is that there is a normal force that keeps the block on the inclined plane. This normal force is exerted by the inclined plane on the block, and it counteracts the effect of the weight of the block. So in this particular case, so we want to ensure that the forces in this direction are zero, and that happens because the block is neither moving this way nor is it moving that way. Therefore, we can say that Fn here equals mg cosine theta. So now let's see what other forces act on this system. So if you look at the friction force essentially acts upwards. It acts in this direction because the tendency of the block in this particular case is to slide downwards, and friction opposes the motion of the block. So the friction force here which acts upwards along the inclined plane is mu times Fn, and that equals mu times mg cosine theta. So what we see here is that this is the force that acts along the inclined plane and it's downwards. So we write that down. So the downwards force of gravity along the inclined plane equals mg sine theta. So we have one force that's acting upwards and the other force that's acting downwards. So the net force downwards equals mg sine theta minus mu mg cosine theta. And by Newton's second law, that equals mass times acceleration. So we can rewrite this expression by cancelling out the masses, and we can rewrite acceleration equals g times sine theta minus mu cosine theta. If you see here, the condition for the block to be stationary is when the force acting on the block along the inclined plane is 0. If the net force here is 0, which it means that the acceleration is 0, and therefore if acceleration is 0, that means that g times sine theta minus mu cosine theta is 0, which can be rewritten as sine theta equals mu cosine theta, and we know that g is not 0, and we divide by cosine theta on both sides. So we get this condition that sine theta divided by cosine theta equals tan theta, and tan theta equals mu, and theta equals tan inverse mu. Under the condition that there is a friction coefficient of value mu, and the theta is related to that by tan inverse mu, if this condition is satisfied, then the block will not slide down the inclined plane. So now we are back to the last problem, and then we want to know if at all the block does move, then that is when the condition of stationarity is not satisfied. So there is a net downwards force. So under what condition, okay, does the block slide down? Okay, so theta is obviously greater than tan inverse mu. And now how long does it take? So one of the equations we want to add right here is S equals u times t plus half at square, where S is the distance traveled, u is the initial velocity, t is the time, and a is the acceleration. Now if the block starts from rest, we know that the initial velocity can be regarded as 0. So we can rewrite this expression very easily as S equals half at square. And S here is equal to the length that the block needs to slide. And this equals to L equals half, and we substitute the value for acceleration. So that equals g times sine theta minus mu cosine theta times t square. So what we can do is we can rewrite this expression as 2 times L divided by g times sine theta minus mu cosine of theta, and we take the square root of that. And this is how long the block takes to slide down the inclined plane. I hope this short lesson has given you an idea of how the dynamics of a block sliding down the inclined plane works. Thank you.